Now we will study a particular case of self-supervised learning that is called this energy-based model. And the goal here is to learn a distribution rather than a function. So typically we tend to think of y as a function of x. But for instance, in this dataset, uh, given an x, there are three different y's that can be equally likely. So rather than estimating y as a function of x, we can try to learn a distribution of the joint distribution of x and y. And this is useful in generative models and in anomaly detection. And here I'm giving you links to more specialized literature on it. So the goal is to learn the joint distribution of x and y, or maybe the marginal distribution of x and y. So y given x, the conditional distribution of y given x. So for doing that, we will describe this as this kind of Boltzmann distribution probability function. And this Boltzmann, they have an energy and they have a normalizing constant that is called a partition function, so that this is a true probability distribution function. So the thing to learn here is the energy. So the energy is the one that is parameterized by the neural network parameters. And it is a joint distribution. What is the energy of observing simultaneously x and y? And sometimes it is convenient to introduce a latent variable that is later marginalized. So we still want to learn the conditional distribution of y given x, but we will do it in two steps. So the first step is x. It will produce a latent space, and then y. From the latent space we will generate y. And then this energy has three components, x, y, and the latent space variable, and then we marginalize over z. And the same for the partition function. We have to marginalize over y and z. Okay, so let's study the normal ones without the latent space. So these energy-based models, they try to learn following this contrastive divergence training. So we will have two kind of sets, or two kind of pairs. So we will have the XY pairs coming from our training data, and we will have these X tilde, Y tilde pairs coming from a simulated probability distribution. Both probability distributions will come from the energy function that we are learning. So this energy function, we will compute the gradient, and this gradient, we will try to minimize the gradient of the log likelihood with respect to this contrastive, so this difference between true training samples and random training samples. So how do we generate random training? So random training samples are generated in this way. So this way is called a Langevin dynamics sampling. So the thing is, we will generate, so we will start with random vectors coming from a Gaussian or a uniform distribution, and then we iterate for a few iterations, and then for these few iterations we will update our drawn samples by trying to make them more likely. So this equation here, they try to make the random sample to be more likely with respect to this energy. So we try to make them more likely with respect to the energy. So if we iterated a lot, really a lot here, then we would converge to samples that they look like very much like the X and Y true training samples. So we will iterate for a few iterations so that they get somehow similar to X and Y, the true X and Y, but still they are sufficiently different so that the neural network can still differentiate between the two. And this is this differentiation. So we try to estimate an energy. So the neural network, given two training samples, will have to produce a number, that is the energy, and this energy has to be small for true training samples, while it has to be large. This is what by this negative sign. So it has to be large for samples that are not coming from the true training samples. And here we have some applications of them. So here we have object recognition. So given an image and a set of labels that we can try. Then we want this energy to be small when it has the correct label. Here it is the same. So if we have different words and we want to say that the word class is a noun, then we can try here different labels like noun, adjective, verb, whatever. And then these energies have to be small when the two labels match, or when the two tokens match. And here it is the same, image restoration, so we can produce larger, higher resolution images. Or we can have, for instance, here generation of input data. So this generation of samples, negative samples. So once you have converged, now you can iterate. So once you have converged with the energy, now you can use that energy to generate samples from that energy distribution, such that they look really like the original data, that is the samples from the original training data set. Okay, and one particular case of energy is these restricted Boltzmann machines. And the restricted Boltzmann machines, you can think of them as having some visible units, some hidden units, and then the energy of any particular combination of X and Z is computed in this way. And then the network, the parameter of the network are the W, the B, and C. So deep belief networks is a particular case of neural networks in which each one of the pairs of the layers, they are interpreted as a restricted Boltzmann machine. So we would go from the input features to the output to this layer set 1, and then from this set 1 to set 2, and we have to learn these energies, and these energies are split into two layers. So I'm just writing the first two, but it will continue. So the energy between X and Z1 is given by this formula. The energy between Z1 and Z2 is formula. Z2 and this layer would be another formula. And then we have the feed-forward neural network, the standard one that we normally have in dense layers, in dense neural networks. And then the whole thing would be named a deep belief network. So this would be all for these energy-based machines. and see you in the next video.